Hey everybody, welcome back. Today we're going to be going through the process of balancing the rotating assembly on the 350 Pontiac engine. In the interest of full disclosure, I want to point out that balancing is a newer process in our machine shop, so I'm open to suggestions and advice on how to lean out and improve this process for the future. To start with, we want to weight match all of our pistons and piston pins, so I started by checking and recording the weight of each pin, followed by doing the same thing on the pistons. The pistons we're using are a stock replacement aftermarket cast piston, and as such, the castings can be a bit further off from the factory when compared with a set of forged or billet pistons like you might see in a high-performance, high-dollar application. With each of the pistons having been weighed individually, it looked like we were coming in at maybe around 2 grams difference across all 8 of the pistons. The piston pins were also a little bit different from each other, so I went ahead and took the heaviest pin with the lightest piston, the second lightest with the second heaviest, and so on, just to get us a better starting point before we start actually doing any modification or material removal on the pistons. In an ideal world, you want to be removing as little material from the piston as possible, because more material to remove means that the job is going to take a larger amount of time, and if you need to remove excess material, you may run the risk of weakening the structure of the piston. With the pistons and pins paired, we're going to go through again and record the weight of each assembly. Once we know the lightest piston and pin assembly, we're going to remove material from the other pistons to make them weight matched within a reasonable tolerance. How you decide your tolerance really depends on what you're trying to achieve with the engine and what the application is. And in the case of this stock 350 Pontiac, it's hard to say whether or not a couple of grams difference in the pistons would really have a noticeable effect, but it doesn't really take that much time to get them closer. With around 1.5 grams difference, it won't be too difficult to get these within well less than half a gram, and if not closer to within 1/10 of a gram. And this is kind of where I need some advice from people on what tools really help make this go fast. I know some people put the pistons in a mill. Here I'm just using a little burr for aluminum, but it's kind of coarse and doesn't leave a great finish. So I came back with one of our Dremel tools with a little sanding disc on it to kind of clean that up a little bit. And again, where we're removing material here is somewhere where it's not going to have any structural effect on the piston. Obviously, we're not going to be out grinding on the skirt or, taking a ton of material out of the boss around where the piston pin, is supported. I also did my best to grind evenly from both sides of the piston, which, again, without having any hard data to test, I don't know how much of an effect that really has when we're talking about, less than 1.5 grams, if not, less than 1/10 of a gram. So let me know what you guys' opinions are on this, because like I said, I'm new to the balancing process and I'm learning, but I'm just trying to do the best that I can without wasting time doing, obviously, way more than what's really necessary, especially in an application like this. There you saw across all 8 pistons we're within about 1/10 of a gram, so now we're going to move on to balancing the connecting rods. This does get slightly more complicated than balancing the pistons, because not only do we have to weight match the entire weight of the connecting rod, we need to weight match both the big end of the connecting rod and the small end. So the fixture you see there allows us to weigh just the big end of the connecting rod when it's set up the way that it is right now. So I went through and recorded all of the weights of the big ends of the connecting rod so that we can start there and go ahead and do some grinding on the balance pad there that you see. Since these are stock connecting rods, again, they have a lot of room there to make adjustments on the balancing. And obviously this fixture has to be set up pretty well, and I know it looks kind of janky there with the blue tape holding everything down, but that's just because I haven't gotten, a dedicated space set up in the shop yet, because we're kind of doing some rearranging to get everything set up. So eventually I'd like to have something more secure looking than this, but this worked very well in the meantime. And here again, obviously we cannot add weight to the lighter rods, so we're grinding material off of the balance pad of the heaviest rods until they match the weight of the lightest. And this is another thing where our belt sander that we have is not really optimally set up for this, especially on these rods here that it was kind of difficult to get at the balance pad without grinding on the rod bolts and the nuts. Actually, I was able to get it done. It just required a little bit more work and a little bit more care taken to make sure that I wasn't grinding on the rod bolts or the rod nuts. As you can see, I'm also flipping the connecting rod every so often so that I can make an attempt to grind pretty evenly on both sides again. But if anyone has advice on what type of sander they use when balancing connecting rods, let me know that in the comments as well. For a good little bit of grinding on the big end of each of the connecting rods, we were able to get them within about 0.2 of a gram there, which I think was perfectly acceptable as a starting point. So now we're moving on to weighing the small end of the connecting rod. So you can see I did a little bit of changing there on the fixture so that we can weigh the small end and get an idea of how much we need to grind off of each of the balance pads on the small ends of the connecting rods. And this is a lot easier to grind the small end of the connecting rods because I'm not worried about hitting the rod bolts or the rod nuts there, and I can kind of just rock it back and forth there and get a nice even grind across that entire balance pad. Again, obviously this is kind of the most labor-intensive part of the balancing process, at least in my book, and as I'm going through, I'm checking the weight, coming back, grinding a little bit more, checking the weight, kind of letting everything cool because you don't want everything to get super hot. It is really just a bit of a process that there's not really a lot of science to it. It's just, doing some grinding, going back, checking your weight, and just getting a feel for, how much grinding equates to how many grams. So once I had the small ends of the connecting rods weight matched within our tolerance, I went ahead and double checked the big end of the connecting rod as well as the overall weight, and I just had a couple there that I wanted to do a little bit of fine tuning on, so I went ahead and did just a tiny bit more grinding to get them really close. They came out really well, so now we're going to go ahead and weigh one of our rod bearing shells as well as one of our piston ring sets, so that we can go ahead and compute our bob weights, which are going to be used to simulate the weight of the piston and connecting rod assemblies when we balance the crankshaft. Our bob weights factor in the big end of the connecting rod and the rod bearing times 2 rods per crankshaft throw, as well as a factor of 3 to 5 grams to account for the weight of the oil that will be clinging to the crankshaft inside the running engine. This portion is considered the rotating weight. We also have to factor in the reciprocating weight of the rotating assembly, which includes the small end weight of the rods, the piston and pins, and the rings. This is where some theory comes into play, and in general, on a V8 crankshaft like this, a factor of 50% is used for the reciprocating weight. Having made this calculation, we now know what each half of our bob weight needs to weigh, and we can go ahead and assemble the bob weights using various different weights as shown here, and the total weight of the bob weight should be exactly what we calculated. In this case, 2,443 grams. Finally, we're mounting the crankshaft on the balancing machine and dialing in the sensor on the snout of the crank, which reads the angular location of the crankshaft to measure the imbalance. We also have each of our bob weights mounted correctly on each rod throw, as well as the flex plate mounted to this crankshaft, as on the rear end, this crankshaft is externally balanced. On the front end of the crankshaft, it's internally balanced, which means we don't have to have the harmonic damper mounted when balancing. This is telling us that we are 18 grams out of balance here and 22.5 grams out of balance over here. Unfortunately, our balancer doesn't have the drill press set up on the machine yet, so we have to move our setup to one of our other machines to do our drilling. But we did input the drill bit size that we're going to be using, and if I hit this button here, this is telling us that at 41.5 degrees on the left side, we need to take 17.9 grams, and we need to take 22.9 grams at 3.5 degrees relative. So I've got this rotated for the right side because we're going to take the heavier side first, and then we'll spin it again and go from there. And if I hit this button here, it tells us that we need to drill that hole to 0.26 inches at that position to remove the correct amount of weight. So we're going to start there. Since we're having to move this setup, I want to make sure that we are aligned perfectly straight up and down when we do our drilling. So I got the laser level out, and I put basically a mark here and a mark here, and then we'll go get it on the V-blocks on the other machine, and we'll make sure that it's perfectly in line so that we can be drilling at the correct position. You got it?
Yeah, I just didn't know how over percenter it was.
Again, we aren't super efficient in this part of the process yet because we are having to do all of this bouncing about between the machines. However, I was able to purchase a very nice set of V-blocks from CCA Racing Products, which made it easy to set the crankshaft up on our boring mill to do our drilling. You always want to start on the side that has the most imbalance, so I kind of started by drilling a pilot hole to a little bit less than the depth that the machine told me, just because I would rather sneak up on it than overshoot it and have to go back and add heavy metal. So I started with the pilot hole and then moved on to the larger drill bit here, and I did have to use some coolant because it just didn't quite want to cut, but everything seemed to work out okay, and we got the first hole drilled.
There's the hole that we've drilled. I have a feeling it's not going to be deep enough, but as you can see, we're still getting the hang of doing balancing here in our shop. It's a new process that we've just added pretty recently, so we're taking it slow and trying to make sure that we get a feel for how things are done, and so let's spin this and see how close we are now. Again, before we were 23 grams out at the location where we drilled that hole. Now I've got that marked as our top dead center point. Just I just re-zeroed there with that straight up, just as a new reference point.
Our balancer does have a calibration arbor, which is used to calibrate the machine at the low speed 500 RPM setting, as well as a high speed 750 RPM setting. But for safety reasons, until the machine measures an imbalance of less than 15 grams on either side, it will not ramp up into the high speed setting.
Alright, so now we can see we're still 21 out on the left. That number changes a little bit when you change everything on the right side. So that's why you start with the heavy side and then go from there. But we still have about 10 to remove on the right side.
At this point in the process, the left-hand side is the heavier side, so we started our material removal there. Unfortunately, the machine wanted us to remove material at a point that overlapped a balancing hole from the factory. And since this really wasn't a good option, we drilled 2 holes to a shallower depth on either side of the factory hole where the machine had wanted us to remove the material. Since we were also still slightly heavy on the right-hand side, we went ahead and took the hole that we had originally drilled a little bit deeper just to, make better use of our time while we had it set up on the boring machine. So at this point, you can see the 2 holes that we've drilled on the left side, as well as the 1 hole that we've drilled on the right-hand side. And we're going to spin the machine again, and at this point, it's going to ramp up into that higher speed setting where, according to the manufacturer, it picks up the imbalance a little bit more accurately. And with that, we've come out at an imbalance of 0.2 grams on the left and 1.4 grams on the right. For reference, a dollar bill weighs just under a gram. So with the imbalance that we still show, it would be similar to if you took that dollar bill and taped it to the outside of that counterweight at that location. And at this point for the stock application, chasing down any further is really a situation of diminishing returns when you take into consideration the fact that there are far too many variables that affect the true balance of this crankshaft, like the dynamic weight of the oil on the components, differences in power from each cylinder, and a slurry of other factors. Having come to a number that we were happy with, I went ahead and put the harmonic damper on this engine, and even though it's supposed to be neutral balance, I just wanted to double check and see if it really did change anything. And in this case, it barely changed by 1/10 of a gram, which we are considering satisfactory. With that moving forward, we took the bob weights off of the crankshaft, and we're getting ready to polish the crankshaft, so I wanted to give it one more wash here before we did that. And I went ahead and put it in the spray cabinet, washed it once, brushed out those holes again, as well as rinsed them out as you just saw, and blew it off with the compressed air to get it nice and clean and dry before we get it back in the crankshaft grinder. I did have a few people comment on our crankshaft grinding videos questioning us on the direction that we have the crankshaft mounted in the machine, because depending on the direction that you polish and grind a crankshaft, you're actually raising little microscopic burrs on that crankshaft surface, which, if they are ground the wrong direction, can actually tear up your bearings prematurely. The process we use is what's recommended by Mahle Aftermarket, who is the manufacturer of Cleveite bearings that we often use. I'm going to go ahead and link an article that describes this process in the description, but I'll give you the overview here. The end goal of the finished crankshaft is for those burrs to be laid over such that as the crankshaft turns in the bearing, they stay laid over and do not catch on the bearings as shown in this photo. Now, with the crank mounted the direction you see here, and with the grinding wheel turning the direction you see here, the burrs end up laid over in the direction shown here. Now, I know what you're thinking. Hey, that's the wrong direction. Those are going to eat up the bearing. And you are almost correct, but we still have the polishing steps shown here. While the crank is still rotating the same direction in the grinder, the belt of the polisher is moving at a higher velocity towards the user. This helps aid in removal of many of the burrs that we're talking about, but the ones that are left behind end up being laid over the opposite direction that they were in grinding to the correct direction as shown in this photo, which results in the goal that we described in the first photo shown here, which is the best case scenario to avoid premature bearing failure. Now, this is something that changed over the years, and it's not the same direction that it used to be done. But considering we trust Mahle's bearings and we trust their advice as a bearing manufacturer, we use the process that they recommend in that article, which again I have linked in the description. To finish off the polishing of the crankshaft, Dad went ahead and switched to a little bit finer belt to really get the perfect polish that we're looking for there. And it's important to note that when you're polishing, you're not removing hardly any material at all. It's very, very slight amount just to get that finish from grinding to a nicer surface finish. He did also go ahead and touch this rear main seal surface just to get it as nice as possible, and you end with just blowing off the crankshaft, making sure that it's entirely clean, including every single one of those oil holes that runs between the rod journal and the main journals. At that point, our crankshaft is ground, balanced, and polished, and we're going to go ahead and mount the connecting rods to the pistons to wrap up this video. So I went ahead and laid out all of our pistons and connecting rods, and this is the fixture that we use to set the stop on the pins so that we get all of the connecting rods installed centered on the pistons. It's also super important to go through and make sure that everything is laid out correctly, so I like to lay out all of the pistons in the same exact direction, and then I'll lay out the connecting rods whatever direction they need to be. So there I've got one bank one direction and the other bank the other direction, because the connecting rod does have to be mounted in the correct orientation on the piston. Here I'm going through and just putting a little dab of oil on each of the pins before we get them installed, as well as I like to take the torch and just really quickly just heat them up just a little bit. That helps the aluminum expand and make everything slide together really easily. So I've got the rod torch getting heated up here, and go ahead and get that flame going and get the connecting rods in it. You do one at a time, and they take just under 20 seconds. Any more than that and you're really just wasting your time and getting the rod too hot. So at 20 seconds you pull it out. That pin has the pin end of the rod has heated up enough so that the piston pin will slide right in, and almost as soon as it's in, it's going to start cooling and that pin is going to be tight on the piston. After the first one is mounted, I go ahead and double check that my stop is set correctly, and that used to be something I struggled with, but as I've mounted more and more press fit pistons, I've gotten pretty good at setting the stop at the correct position so that the connecting rod is centered on the piston. And it's pretty much the same process. My dad's a lot faster at it than I am. I like to really just do one at a time, but my dad can run through these things and, whatever, 20 seconds times 8 connecting rods, he'll be done with them just that quick. But once they're mounted, go through and just double check that they're all correctly oriented on the connecting rods. These Pontiac rods have an oil spurt hole that needs to be pointed up towards the camshaft in this case, as well as double check that they're centered well on the piston. Finally, just for fun, just wanted to go through and double check that each of our piston and connecting rod assemblies were roughly the same weight. So grabbing that first rod there and setting the 0 on our scale and just going through and weighing each one. And I think we came out at maybe around 0.3 of a gram overall, which I would say is pretty dang good for this mostly stock 350 Pontiac. If you made it to this point in the video, I want to say a big thank you to you guys, and if you don't mind, give it a like. Make sure you're subscribed if you're not already so that you can continue following along with this series, and I hope that we'll see you on the next one.